Welcome, everyone. Good evening. Welcome as everyone's joining in. Welcome back for another virtual science camp in the Particle Physics for Kids series. I'm really excited to be starting another month today, and especially for our guest host, Marco. So I might have mentioned to some of you, and some of you joining actually know Marco and myself as well from CERN when we were together at International Teachers Weeks. And that was my second time visiting a nuclear research facility. And I learned a lot there. But surprisingly, it was only like a week or two after I left CERN, Marco sent me some stuff on bubble chambers. We kept in touch, a bunch of us. And I was going through all these resources, a number of which were in German. And finally, a lot of parts of detectors made sense to me. And it's surprising that I had visited CERN, I had visited the Joint Institute of Nuclear Research, and there were a lot of details still left to learn from Marco. So I was really eager to invite him to come on as a guest host to talk about detectors. He'll use bubble chambers as an example, but I'll let him tell you all about that once I turn things over to him. Just before I do, to mention, if you have questions during the session, it's best to write those in the chat. I'll keep an eye on things. If you feel like turning on your microphone to ask a question, just write in the chat that you have a question. And when I think it's a good time to interrupt Marco, then I'll stop and we'll call on you. Or if you want me to just read your question for you to Marco, then I'll do that as well. Also, just as I'm introducing everyone, feel free to introduce yourself in the chat. If you want to mention where you're from or anything like that, feel free to say hi to everyone like that. I think that's everything I wanted to mention. So without further ado, I'll turn things over to Marco. Welcome, and thank you again for joining us for this.
Okay, thank you, Michael, for giving me the chance being here today. And thank you for giving me the chance speaking to so many people. I see 22 participants today. And I'm getting a bit nervous after this introduction, Michael. Thank you so much for putting a bit of pressure on my shoulders. But I'm going to do my very best and hope to make things as clear as they came to you, Michael, after your visit at CERN. So maybe I just introduce myself before I start. You may hear my accent. I'm a teacher in Germany, and I teach mathematics and physics and informatics. And yeah, in 2018, I met Michael at CERN, and I somehow fell in love with particle physics and with detecting and everything about these tiny little things we are going to talk about today. And I prepared some slides I want to share with you. Just give me a second. Okay, I think you can see the slides now. Michael is...
Yes, coming in clear.
Okay. So I tried today to make the invisible visible. I don't know if I can do, but some people at CERN and other particle physics laboratories did very well because they invented things that are called detectors. And I want to talk about the basic idea of particle detectors and want to give one example about the detectors, which is the bubble chamber. I like this one very much because it's a detector you can introduce at school easily. And I see many teachers around here in this list, and maybe you get ideas for your lessons when teaching particle physics. No? So let's start. So if I talk about the invisible things in our universe, I'm talking about elementary particles. And this is what the particle physicists are looking for. And they just want to answer three very simple questions. Where are we from? What are we? And where are we going to? So the questions are very simple, but the answers are not. And I think all those three questions are not really answered for today. And if I say we, I don't mean you and me here in this Zoom conference, but I mean all of the universe. So fundamental questions, which I won't answer today, because if I could, I wouldn't teach at school. I would have a nice house somewhere on a remote island and would have a good life if I could answer that. But let's go back to these slides. There is a problem about answering this question. No one has ever seen such elementary particles with your own eyes. And why it is really easy to understand. If we go back in history, we go about 500 years before Christ was born. the Greek philosophers were thinking about matter and what it is made of. And they said, okay, we have tiny little particles. Some said they look like small cubes. Some thought they looked like triangles, like little pyramids. So very strange ideas of how matter and the atoms look. But it came a little bit clearer in the early 20th century after the electron was found and after Rutherford said, okay, I have an idea how atoms may look. We have a nucleus, which is a positively charged thing, and we have electrons, which are negatively charged, and they are circling around this nucleus. But this is not the end. We can even get a bit further into these atoms. In the 1960s, the quarks were found, and scientists found out or made a model of matter where they said, okay, all protons, all neutrons, which you find in the nucleus, are built of quarks. And so you can see, if you look from the left to the right, we can maybe imagine something about the size. This, we can't say how big they are. But we can say, okay, atoms are at maximum about half a nanometer. So 0.5 times 10 powers by -9 meters. And if we go deeper into matter, and we do here at this time, we have to, well, make this number much smaller. And if we talk about elementary particles, we talk about a size of 10 powered by -18 meters, which is incredibly small. So just to imagine this, you can imagine half a meter very easy. So half a meter, maybe, oh, I can show on my camera something like this, but you can cut this half meter into 1,000 equal particles. Then of course you have half a millimeter. And I think half a millimeter, everyone can imagine. You can look at your ruler, you can see the millimeter, half a millimeter. Okay, we can see it with our eyes. But then we can take this half millimeter and cut it again into 1,000 equal parts. And then we are still larger than this size here. We have to cut again into 1,000 equal parts. So we cut half a meter into 1,000 parts, each part again into 1,000, and each part again into 1,000. And then we are at an incredible small scale at 10 powered by -9 meters. And if we want to go to the 10 powered by -18 meters, we have to do this again, cutting each part of this we just got a second before into 1,000 equal parts, and into 1,000 equal parts, and into 1,000 equal parts again. So it is incredibly small. No one will ever see this. And this is a problem the particle physicists have. They want to see it, and they want to try to make these particles visible. And I'd talked a lot now, and I just want to go to the first activity of this virtual science camp. If there aren't any questions, Michael, are there questions?
No, there aren't any questions that have come up yet. If anyone thinks of any questions, remember, please please write them in the chat to let us know.
Mm-hmm. Okay, it does not seem so. Then I'm going to write a link into the chat. And this is a video CERN made once, I don't know when, but it shows very well about what we are talking here, about how small matter is. And I just want you to click at this link and watch this video. It takes about 2 minutes, and I think we can meet again here in 2 minutes after you watch the video. Then, okay, let's get on. And how can particle physicists see those tiny little things? Well, I just told you they have something which is called detectors. And if you go to the Latin language, there is a word which is called detector. We say in German, maybe English pronunciation is a bit different. And I think Italian pronunciation, oh, I see Maria is smiling, is completely different from what I said now. So, but this word here, however you pronounce it, it means to discover, to find, and to trace down. And this is exactly what particle detectors do. And so I want to do one next activity with you. So everybody, and you see I printed body in capital letters, has and uses detectors every day. So I want you to write me a private message in the chat where you give me one example of a detector you have at your body and what this detector detects. So please write this in a private message.
And for those of you who aren't used to writing private messages, just in the chat, there's a blue box that says to everyone, and you can select Marco's name. He's a co-host, so his name will be near the top.
Yeah, and I already get the first answers. Oh, that's a good one. Okay, thank you so much for all these perfect answers. Just to summarize what you said, I somehow knew what you are going to say. We have, of course, our eyes, which detect lights. We have our mouth, and we can detect with our tongue. We can detect the taste, so we can decide if something is sweet or sour or salty or umami. We have our skin and our nerves, maybe on our fingers or everywhere on our body. We have our nose, which can smell. And of course, we have our ears, which detect sound. And someone wrote in the chat, so every sense we have is a detector. And this is absolutely correct. And the good thing about those detectors is we have many of them. And luckily, we all have a brain which can make use of the information these detectors give to us. So our brain is something like a computer which gathers all information those detectors are collecting. And this is a conclusion we can draw about every particle detector or every detector. So we have many on our body, and every detector is doing a special thing. I just want to give an example. If you have a fish lying in front of you, your eyes cannot, of course, detect the smell of this fish, but of course your nose can. And you can smell and say, okay, I maybe should not eat this fish. But how can you be sure? Well, okay, you can look at this fish and you can see, oh, he looks a bit ugly. I should better not even touch it. But if you do, you may feel it's very wobbly and consistency you don't even want to touch and you don't want to eat, and you throw this away. So each detector is detecting a special thing, and our brain is like a computer which makes the information and well, which makes us decide what we should do next and what we can do with this information. Okay, that's quite a nice classroom activity, and you can lead younger students to detecting in this way. And maybe you can also use, if you are a teacher, this picture. And I found this lovely picture on Pixabay where you can get many free pictures, but I like this especially because what we see there is a large particle detector, in fact. And I want to ask you, which information does this picture provide? And yeah, you can just say it loudly or write it in the chat. I'm looking forward to your answers.
So again, you can either write your answers in the chat or feel free to turn on your microphone to shout out an answer. So we're getting some from the chat. Stuff leaves traces.
Mm-hmm. And I also got three private messages. One says there is something about a direction, and there were a lot of people walking. The sand is not dry. Okay, people on the beach. We have a direction. We have many humans. Many people have been there. So we get a lot of information. Someone says animals, okay. So we get a lot of information from this picture. I see people walking there. No, I don't see people walking there. Actually, we don't see any people. We don't see any animal here, but we just see their traces. And this is a second thing detectors do. They just try to scan for traces. And we can't say if this dog here was a black dog or white colored dog or maybe a heavy dog. And we can't see if this person here was a man or maybe a heavy woman. We can't say if the person wore a black t-shirt or a red t-shirt or whatever. We only can say, well, there was a person, and maybe we can say, okay, this one was definitely heavier than the person who left these footprints here. So we can see traces and we can draw a lot of different conclusions. The direction is here as well. And that is a thing which detectors also do. They can detect traces, and that is an important point. They don't see the particles. They don't, well, we can't see them, but we can see their traces. So we can't say if we see a trace, well, which particle it was. Maybe if we don't get any more information, we can't say. But we can see there was something. We can't see that particle, but we can see it was there, and we see it left a trace. And I will show you the next thing. We just started by using, well, everyday's pictures. We see every day, but this maybe you haven't seen, because this for now is the real detector. We are now going to make a step towards the particle physics. And this one you see here is a bubble chamber. If you ever was at CERN, you have seen it there. If you haven't been there, you have to go there, because this is part of an exhibition which is public, and you can go there and you can see this lovely thing which looks like a rocket but actually is a particle detector. And this is what you saw on the introductory slide, is a bubble chamber. And it consists of two parts, this one and this one. This is a piston which is put inside from below. And I give you a bit of data about this one. It's quite heavy. Why is it moving again? It is 26 tons. So it's not easy to get away from there, or I think it was quite difficult to get it there because it was not standing there in original. And this machine was working between the years 1973 and 1984. So it's quite an old machine, quite an old detector, but this makes it somehow very cool, because everything which is a bit older, I think it's much more easy to understand compared to these modern detectors like Atlas or CMS. And this bubble chamber, in fact, was very important in the history of particle physics, because the scientists proved the existence of some particles they didn't know before, and also started a lot of research in neutrino physics. So it's a very important machine, and we are going to look at how this machine works. I tried the best to sketch it out, to make it very simple. I hope it worked a bit. So you see this blue box, this is this one, okay? And you see this, it's a bit violet. This is a piston which is put inside and which can move up and down. So what else do we have? We have cameras and we have flashlights, and obviously cameras are there for making pictures. And I will show you a few pictures of the cameras later, which they made. And I think you will recognize them from some slides earlier. So inside this big box is a liquid, and we have a beam of particles, which the physicists are going to observe and get information from them. And one very important thing, you will never find a particle detector, at least a good working one, without a magnetic field. So we are going to talk about all this in the next slides. So if we have the real machine, it's not small like this, but we have 30 cubic meters of liquid gas inside, for example, hydrogen. And this machine you saw earlier made 6.3 million of pictures on 3,000 kilometers of film. In all in all 22 experiments. So it produced a lot of material in its lifetime. And this, of course, is a lot of data people had to work on. And if you compare this picture to a thing you know, maybe you can imagine this a bit better. We are all talking about vaccines for or against COVID-19, then you know the syringes. This one looks not exactly like, but very close to this one. And if you want to understand how this machine works, you can use this syringe in this picture. And I'm going to show you now in this slide how a bubble chamber itself works. We are going to talk just a few minutes about this because I want to dive deeper into the matter and look at original pictures and work on original data with you later. So in this experiment, I'm going to show you as a video. You simply need, you can do it at home, a syringe. I have one here. And you need warm water, which you fill into the syringe and you press out all air. And then you take your finger and put it on top so no air can go out or go in. And I hope this video works now. Yeah, it seems so. What you can observe is this. I hope you can see something because I see only on my second screen, not on my first. So I pull out the piston a bit. And I try to remove all air which is inside. There was still a little air inside. And I try again. And I think in this part of the video, you should see clearly many bubbles. And what just happened there, I just boiled water just by using a little syringe from plastic. And the reason why it boils is that I reduced the pressure inside the syringe. And you know, maybe if you ever went to Mount Everest or other high mountain, you can boil water by a temperature which is quite lower than the 100 degrees of Celsius. And this is nearly exactly what happens in this big detector. So this piston, which I showed you in this sketch, is pulled out and pressed in again. So the liquid inside was brought to a temperature which is very close to the boiling temperature. You don't want to make this boil because then you obviously see only bubbles inside and you can't see anything but bubbles, but it's close to this temperature. And if you now take electrically charged particles and shoot them inside, they give some of their energies to the liquid and bring the liquid to boil locally. And what you get then is a picture like that. You get many, many bubbles which are along the path the particles take. And I promised you, you will see a picture in this session which is similar to the one you saw before. This is nothing different than the footprints we saw on the beach picture before. And this is an original data this bubble chamber took. I got this at CERN. And we are going to explain, well, a lot of things we see here. But I see now some messages in the chat. Maybe is there a question? Then we can stop here.
Yeah, there was a question about the labels under the bubble chamber sketch. And then another participant seems to have explained that the left one was the liquid and the bottom one was the beam. But if possible, just so that's clear for everyone to see, can you go back to that sketch so it makes sense to them with the mental picture?
Yeah. Okay, maybe is this so this which is sketch blue is the liquid. It's always faster than me. So, okay, this in this box, of course, it's full of liquid. And this is the beam which is coming in this sketch from below, which is just shot into the chamber to leave the traces. Was this the question?
And in case it makes it more clear, hopefully more rather than less clear, relating to the picture of the bubble chamber at CERN, this would probably be flipped upside down because you were saying the piston was going from below, right?
Yeah, honestly, I think in this situation, how this bubble chamber is set up, the piston should move from down to top. So, but if we look at the pictures of the traces, I'm going to explain later why I turned it upside down. It has a special reason because we will see the beam is coming from below and going up. That's why I sketched it like this. But the real machine is just flipped by 180 degrees.
And it's possible, and I have no idea. I don't know if you know, but was the real machine flipped 180 degrees while it was operating, or like, do you know what orientation it was in when it was in use?
I don't know for sure, but I think it was like this.
Okay, yeah, because that's something I'd have absolutely no idea about.
So I think it would work if it flipped by 90 degrees or even 180 degrees. I think only if you only have to reduce the pressure. And I think it does not matter if the beam comes from maybe here to there or from top to bottom. I think it does not matter how it is orientated. I think this is an engineering question. What is more stable, because I think you have a lot of vibration if you move this piston, which is about 1.5 tons. This will vibrate heavily, and so it's an engineering problem how to set this one up. And I think this is the best solution, like this in this picture.
And the orientation wouldn't matter for the bubbles floating upwards because everything is done at a quick enough time scale that that wouldn't come into play, right?
Absolutely, yeah.
Excellent questions, guys. If you have more questions, please keep asking them, because that can help not only your understanding, but there's probably other people wondering the same things if you're wondering something too.
Okay, then let's jump forward. We saw this one, we saw this one. Boom, boom, boom. We saw this one, and we stopped here at this point. Okay, so as I told you, this is a picture taken by the bubble chamber, and here is, I wrote this answer of your question down, why it's opposite to the original thing. The beam is coming from here and it's flying up. So in my lessons, I always do it like this in my sketch. I just show the beam coming from below, and I just skip that question how this chamber is orientated. So just for the practical reason, this is the direction of flight. Every picture you see today, particles coming from below and moving to the top. So just to make it a bit more easy. And so you can see a lot of things are happening here. And this is one of the questions I want to answer in the next minutes. And I hope we don't run out of time, because I see it's already late. One question is, you see many traces moving straight. This is the beam, and many traces moving like this. They are quite curved. And I just want to briefly explain why. And so if it's too boring, just give me a sign and we can make this a bit faster. I don't know how many, if you are all teachers, we can skip that one, but I don't know if you have students here today. Then
well,
maybe
there's definitely a mix. So I'd say we're about half teachers. The youngest students are about 10 from Paris, but they're really bright and have attended most of the sessions so far. So don't worry about going slow for them. And then the average other students are roughly 14 to 16 age range.
Okay. Okay, then let's have a closer look at this. And I just zoomed in a bit, and I found an event. I think it's quite a cool one, because we can explain a lot of things, a lot of facts particle physicists found out in the last year on this single picture here. So the first question I wrote down on the last slide is, why are some of the curves bent? If you look carefully, I just follow this trace with my pointer. This is a curve. And this one also, and this one is slightly curved, but maybe you can't see so well. This one is curved, and I just didn't see that one. This is obviously really much curved. And the reason is, I told you before, we have a magnetic field all around this chamber and inside the chamber. And I'm going to talk about this a bit later. You can see some traces are going to the left, or if you follow the clock, you will see, well, it's like a pointer moving counterclockwise, while the red ones are looking like a pointer going like my laser pointer does now, in a clockwise direction. And this is a thing we have to keep in mind. And the reason for this is we have a magnetic field. And well, most of you maybe have heard about the Lorentz force, which is a force which applies to moving electrically charged objects in a magnetic field. And I'm going to explain this rule for a negatively charged particle. Let's say this particle is coming from here. Something is happening here. We will see what happens here later. And if you use your 3 fingers, and I know this rule is explained differently in maybe most countries of the world, I give you my version, maybe you know another one. If you use your left hand and your thumb, the thumb is pointing to the moving direction of the particle. I color-coded it a bit here. So the thumb should point upwards parallel to your screen. And the magnetic field, which was applied in the situation where I took the picture, not I, the CERN took the picture, was pointing outside the paper or the screen. So you have to use your index finger pointing towards you. Maybe you see, so thumb is parallel to your screen, pointing upwards, index finger perpendicular to your screen, pointing towards you. And then I love this in my lessons because all students sit there and do this stuff. And then you have your middle finger, which is perpendicular to the 2 other fingers. And this is the direction of the Lorentz force. Yeah, wonderful, Michael. This is what I see in my classes when I do this. I love that. So you can decide in which direction negatively charged particle moves if it passes through a magnetic field. But on the other hand, you can use your fingers to decide if this particle is positively charged or negatively, because you have your 3 fingers and their orientation is always the same if you put them like so. And then you can interchange. If you have the direction and the magnetic field, you can decide the direction of the force. If you have the direction of the force, so it says if it's moving anti-clockwise or clockwise, and if you know the original direction of flight, then you can decide with your fingers and knowing the magnetic field and its direction if this one is positively charged or negatively charged. Well, this was quite quick. You only have to keep one thing in mind for the next activities. If you follow these traces and it's like moving clockwise, you know they are positively charged in these pictures. And if you follow them and they move like anti-clockwise, keep in mind they are negatively charged. This is all you have to know for the next slides. And let's test that one. I just zoomed in this picture again and found some, I think, interesting events. Let's look at situation 1. There's one particle coming from here, this violet trace. Something is happening here, and we see 2 traces, one blue and one green. So let's test this system. Please give me a thumb up if you think the blue trace is from a negatively charged particle, and a thumb down if you think it's positively charged. So you can use your fingers or just keep in mind how the clock goes.
Oh, and also for giving a thumbs down, Zoom doesn't have like a thumbs down icon like the thumbs up icon reaction. So for people who don't have the webcam on, we can pick another one like that. Like it could be the no one, like this cross.
Yeah, or maybe we can say no one get a thumbs down, so all said it's positively charged, which is absolutely correct. So I didn't see any thumb down, so all said it's positively charged. And it is, if you follow this trace like so, it's like moving a pointer of the clock, it's clockwise, so this one is positively charged. What about the green one? So Michael, you said give maybe the green symbol or the red symbol.
Yeah, should the red be for positive or negative?
Let's say red is positive.
Okay, red is positive and green is negative.
Yeah. Like in the textbooks, all positively charged particles are painted in red. Never saw any other color for positive ones. So I saw a bit of green, okay, and I saw a bit of red here in the status icons. Okay, this one actually is also charged, please go back, positively, because if you follow this one, it's bent a bit at the end here, It's like, again, the pointer of your clock moving clockwise. So these are two traces of positively charged particles. Let's go to this one. So you see it's slightly curved here. And I just try to make this clear with my pointer again. This violet trace, number one, is it positively charged? Is it negatively charged?
So again, if you think it's positive, put a red reaction. If you think it's negative, put the green yes reaction.
Yeah. So I see a lot of red ones. So again, it's like this. If you follow the trace and it's bent like so, it's like my pointer, it's moving like the clock does. So it's positively charged. And if we go and follow this blue trace, we do the game again. Green is for negative, red is for positive. Okay, I can see green, I can see red in the list. So actually this one is negatively charged. And again, if I follow this trace like so, it's like, well, it's not like the pointer of your clock, it's moving in the opposite direction. And this means this one is negatively charged. So the only thing you have to check, if you follow the traces and if it's anti-clockwise, it's negative. And if you follow the traces and it's like a clockwise movement, it's positively charged. Actually, the same we do in the next activity. I'm going to tell you some special events. I'm going to show you how they look, and you can memorize them. And hopefully you printed out your handout Mr. Gregory sent you with the invitation. You can use this because I just printed what you will find on the next slides, and you can take notes to keep this in mind more easy for the activities. So we do some detective works here on very, very common events. So on this left picture, see here, you see this spiral trace. It's just like a coil, and you saw it in the activity before. This happens very often. You can see it here in this part, you can see it here, and you can see it here. And what actually happens is that the beam is coming from below and kicks out an electron of the atoms of the liquid inside. And I think I told you before, in this bubble chamber, we have liquid hydrogen, which is basically a proton and an electron circling around. And what happens here is a particle of the beam kicks out an electron of the atom, and it coils like this. So it's moving, it's losing energy, so the radius is getting smaller. And this is an event which happens very, very often, but I think it's not so important for the physicists, only for one reason. If you know that this coil is made by an electron, you can know how you can, or how you have to turn your picture, because the slide is transparent, it's a transparent film, and you can look at it from both sides. And so you can decide which was the direction of my magnetic field, and then you know how to look at it. So these are actually used to see the orientation of the magnetic field and get information, how you have to turn this picture. Another thing you just saw a few minutes ago is shown in this picture. I just said it's billiard because it's nothing else than a billiard game. In this case, a particle is coming from here and hitting a proton and kicks this proton to this side, and the incoming particle is reflected to this direction. So what we see is just a collision, just kicking a heavy particle aside and a reflection of the original particle. What you maybe can see is that this trace is quite heavy, quite fat trace. And if you recall this beach picture, you saw these deep footprints from a heavy person. But it's exactly the same here. If you have a heavy particle, like a proton, which is really heavy and really massive compared to an electron, it leaves a very fat trace. So you can say, oh, this was a massive particle, and maybe it was a proton. This is an information you can get from this slide. I just see something in the chat. Ah, Michael, just...
Yeah, just I gave the link if anyone didn't have it printed, and it was handy to be able to look at it in another window.
Yeah, I think it will be handy in the next activity, if you know that. But just let's move forward. The left picture, you saw before this picture where some particle was coming from here and many traces leading away from this one. So this is a collision of a particle which is coming from below and it's hitting a proton of the liquid. And all of you, I'm sure, heard Einstein's very famous equation, energy equals mc squared. So energy is the same as mass. And this is what happens here. You have an incoming particle, which obviously has mass. This particle hits another particle and produces, well, 1, 2, 3, 4, 5, 6 other traces coming from there, if you count carefully. So 6 particles. And the reason for this is the mass of the incoming particle and the mass of the proton, which is hit, is for a short moment changed to energy. And this energy, in the next instance, is going to turn into matter or into mass. And this is why 6 traces are coming from here. So I just say it as if it's a real easy thing. No, it is not. So if you want to dive deeper into this matter, this is quite hard stuff. So I'm just talking a bit about this. But if you don't understand the processes taking part here, it's absolutely okay, because it's, again, really heavy stuff. It's just important you know that you can produce particles by Einstein's equation E equals mc squared. And this is what you can see on this picture. You can see these 2 coils or these spirals here, but if you look carefully, they start here where my pointer is now, and one is moving anti-clockwise and one particle is moving clockwise. So we have 2 particles coming out of nowhere. One is positively charged, and this is this one, and one is negatively charged. And what you see here is something which is called pair production. From energy, which is light, for example, in X-ray, you can produce matter. And the interesting thing here is you have matter. This is this one, the electron, and this one is an anti-electron. If you took part on when was it, about the AD, last Tuesday?
AD was Thursday and Atlas was Tuesday.
On last Thursday, and when we walked around the AD, they talked about producing antimatter. And this is what you see in this picture. You can literally see how antimatter was produced in this bubble chamber. So antimatter is not an invention of Star Trek or so, it really exists. The problem is it does not exist very long, because it will hit matter sometime later and will become energy again. So in this bubble chamber, you see a lot of transformation between energy and mass. And I think we can do a quiz now, because I talked so much. I zoomed in again into this picture, and I just wrote down 3 things. And I just want you to look carefully at this picture and check if you can see some ionization of the liquid inside the chamber, or if you can see something where new particles are produced, or maybe if you see the beam. I just found out you can zoom with your fingers if you want to look closer at the picture here, or if you print it out, the handout, you can find this very picture on page number 4.
And also, if you're using it on a screen, then you should be able to zoom. Like, it depends if you have it in a PDF viewer in a browser, how you'd zoom, but you should be able to adjust the zoom level if it's easier for you that way as well.
And even for a bit more help, I just did a bit of color coding here. So who can tell me what happens here with the green trace? What is happening in the bubble chamber?
And feel free either to turn on your mic or write in the chat if you have an idea what's happening with that green trace.
Exactly. Yeah, I got first private message. Perfectly correct. Yeah. So what you see here is exactly what is written to me in the private message. This one is an electron kicked out by the incoming beam. So this is, I think, this part of the beam of the particles. It's kicked out and spiraling around. What about the violet ones? I think it's easier just to speak in the microphone than typing. So I get many private messages about this event happening here. So well, it's good to make the others not cheating, but writing in private here. So yeah, what you said is yeah, we are producing new particles here. In this, you see there's 1, 2, 3, 4, 5, 6 traces coming from this point. And this is exactly what you said, it's production of particles. I got a question about this. The person who asked if there is some ionization process here. There may be an ionization process, but I think it's more like just producing particles by the beam hitting the proton. So we can't say for sure always. For some pictures I wrote to people I know at CERN, I knew at the University of Dresden who do a lot of particle physics, and they said, oh, we have no idea what happens there. So it can be a lot, but it is producing new particles here at this point. Okay, maybe we look at another one. In this picture is hidden a billiard game. Actually, 2 times it's played billiard here, and of course we have a lot of ionization again. Ah. Okay, I get the first answers in my chat. And a very good question I'm going to answer soon. So I can read, we have electron circles like this one or this green one, and here's one more hidden, it's a bit smaller, one here, and I can see the red and the red, yellow, green ionization billiard game. Okay. I should read your sentence to the end, Marigo. Yeah, of course. Yes, this is the spirals here is the electrons of ionization, and these other two are the billiard game situations. And one of you said, if I go back, this one, this fat trace is made by the proton. Absolutely correct, because it's very fat and leaves a deep footprint. Then I was asked, what are these crosses here? There are some crosses on the picture. And this is a brilliant question. And these crosses are not particles, but they are scratched into the glasses in front of the camera. And there's a simple reason for this. There is not only made one picture at one time. If you recall this sketch of the bubble chamber, I draw 3 cameras there. Actually, in the original chamber are 5 and more cameras. And that has a specific reason, because if you look at a situation from different angles, we have a different perspective. We can do an experiment to prove this. So if you put up your thumb and close one eye and focus on your thumb, and then open the other one and switch back between your eyes, you will see the perspective always changes a little bit. So your thumb is moving a bit, although you don't move your thumb. And you have this same situation if you have not one camera, but 2 or 3 or more cameras. So you take maybe up to 5 pictures of the same situation from different angles, because this movement of the particles, of course, is not two-dimensional. What you see here in this picture is a projection. So we can't say this particle is flying through your screen, just like this, like my pointer moves along your screen. No, this may go maybe into your screen or coming out. It's just a projection. And if you really want to analyze those pictures, you need at least 3. And this is where these marks come into the game. You can put them, as they are a transparent foil, on top of each other. And then you can move them until these crosses are over each other. And then you have something like a 3-dimensional reproduction of the traces. So this is just for using multiple pictures of the same situations from different viewing angles to get more information about all of this process. But it's a fantastic question why these crosses are here. And I think, Michael, we have 1 hour now. I think I should stop here. I had some more slides prepared, but if you look at the handout, you can do this at home and try it yourself. And maybe if you want to know the solution, you know Mr. Gregory's email address, you can write him and you can forward to me and I can answer if you want to send it to me. And we can get in touch about these traces you see on this printout, on this handout you got. And yeah, 2 more words at the end. What I did now in about 60 minutes. At school, I usually have not 60 minutes for this, but round about 3 hours. So if all this I told you was a bit quick and you did not understand everything, absolutely okay, because this is stuff you normally use or need more time to deeply understand it. And the second thing, I wrote down a few links. If you are really interested in looking at the double chamber a bit deeper, the first is a very interesting article about bubble chambers. And the second one is a film where you can see how this bubble chamber was assembled at CERN. And maybe I think there's also how the people worked on these pictures and how they got their informations. And if you want to dive deeper into the specific traces, on this website here, you can find many, many pictures. And the next links I wrote down are not only for teachers, but also for very interested students. And on the first link, you find a complete walkthrough of analyzing those traces. This is very, very much mathematics inside. But if you want to try, give it a try. I like this page. It's explaining a lot and it's going much deeper than we did today. And of course, we have a fantastic school lab with much more activities about bubble chamber pictures for the classroom. And yeah, this article here is also brought by one of these people working at School Lab, and it's more about teaching bubble chambers in lessons. And if you are able to speak a bit German or read German, you can find a great activity using GeoGebra, and you can work on original pictures there, and you can use this program to find out how fast particles moved, and many more interesting things you can learn there about bubble chambers. So I came to my end just now, and I thank you a lot for participating. I hope it was not too quick. I hope you can take some things home from today's virtual science camp, and I hand over back to you, Michael.
Well, thank you, and thanks for that great lesson on bubble chambers and detectors. So like Marco said, oh, before I forget, there's been a question. Someone was asking if we can mail out those links. And I assume that's no problem. You can give me the links and I'll mail it out to everyone after the session.
These links you find in the handout. So if you go to this Google Docs document, you find all the pictures you saw today, and on the last page, you find all the links on the, yes, exactly, on the last page.
Okay, so anyone who wants the links, if you didn't look to the last page of the handout yet, that was emailed to everyone who signed up. If for some reason you didn't get it, just send me an email and I'll get that to you. And like Marco had said, this went a little bit quick because it was fitting a multi-hour session on bubble chambers into 1 hour. So if anything's unclear, that's perfectly fine. But if you started to understand bubble chambers, then that'll give you the essence of what's happening inside any detector. So any detector I can think of. I'm sure there's going to be exceptions to that statement. But if you think of the Atlas detector, if you were with us for the virtual visit last week, or if you see any other big modern detector, what's happening to the traces of the particles inside is going to be the exact same thing. The LHC is much, much higher energy than the beams of particles in the bubble chamber there. So the how fast it curves will be different. And that's one of the reasons why things like Atlas, CMS are so much bigger than the old bubble chamber. But the principle is going to be the same. And that's one of the reasons I absolutely wanted Marco to go over detectors and bubble chambers with us. Because if you want to understand what's happening in any detector, you need to ask Marco to explain bubble chambers to you. So thank you again for joining us. It's been really great having you to go through this for us. And thank you everyone for joining us. It's been great having you guys along. I hope to see you back for more of the sessions. This Saturday, we'll be playing a particle physics game to go over particle identities. It's not confirmed for sure, but I heard back from the person who created the game, and they're going to try and join in the session. They're in Australia, so it's going to be 4 a.m. They didn't make any promises, but should be a good session. I'll be trying out the digital version of it, which I'm in the process of making this week. So no promises that the gameplay will be excellent or smooth, but I'm hoping it'll work out well. Next Tuesday, we have Jeff Wiener back. There were a lot of questions about antimatter and something else, I think accelerators in general. And so his talks on antimatter and accelerators, other talks later in the month from the Joint Institute of Nuclear Research and from Perimeter. So hopefully we'll see you guys back for a bunch more. We've gone over and now I keep rambling. So I'm going to say goodbye. Have a great evening, everyone. Those from CERN ITW, I'll look for a link in our group chat because I hope to see you guys back for another meeting after this. And have a great evening, everyone. Thank you again, Marco.